UMPE ingests an arbitrary subset of 4 map priors: vector, vectorized HD and SD maps, and raster, rasterized SD map, satellite imagery, and processes them via a vector encoder and a raster encoder. The resulting priors are fused with BEV features, supporting both online HD mapping and end-to-end planning tasks. For this work, the prior datasets of new scenes and Argoverse 2 are obtained manually, which include vectorized HD and SD maps, rasterized SD maps, and satellite maps. Vectorized HD maps are processed from the primitive dataset records and the official APIs. Vectorized SD maps are obtained through the scripts of Smurf by accessing the OpenStreetMap API. Rasterized SD maps are post-processed from SD map polylines by drawing each category on one channel and stacking them together. The satellite maps of new scenes can be found published online, but Argoverse 2 cannot. The satellite imagery of Argoverse 2 is obtained from the OpenSatMap dataset published on Hugging Face, which covers the areas of all 6 cities Argoverse 2 needs. Each of its imagery is spliced with 8x8, 64 in total, images, with the center coordinates of each tile provided. So, we can calculate the WGS84 range each whole imagery covers. Then, with the ego WGS84 coordinates of each timestamp, we could search which imagery every ego pose lies in and crop the corresponding map patch. In the vector encoder, HD and SD polylines are SE2, pre-aligned and encoded. BEV queries attend to each source with confidence-biased dual cross-attention. Presence normalized, channel-wise gating mixes sources to produce fused vector tokens Y. In the raster encoder, rasterized SD map and satellite imagery pass through a shared PHY-LM conditioned ResNet, then undergo a SE2 microalignment in raster space. Channel-wise gating yields fused raster token Z. Eventually, the residual fusion fuses Y and Z with a learned scalar alpha, producing XUMPE. As the visualization shows, for the mapping task, models aggregated with UMPE are obviously superior to their baselines. The case is the same in the planning task. Mapping results demonstrate UMPE consistently surpasses others when using a single prior encoder and achieves the highest MAP when both prior encoders are enabled. Despite the accuracy gains, runtime remains comparable to prior work. Planning results show that our vector encoder already yields a large L2 drop, while the raster encoder also helps. Combining both in UMPE gives the strongest improvement, outperforming all prior injection methods. Source robustness and compositionality of UMPE are assessed by evaluating subsets of the 4 priors on map TRV2. When we toggle to a single prior at test time, UMPE outperforms models trained only on that single prior.